night, 25th November 2025, the Matera Laser Ranging Observatory in Italy recorded something that should not have been possible under any known lunar physics. Their routine procedure had not changed for decades. Fire a precisely calibrated laser pulse at the retroreflectors left on the Moon by Apollo missions, wait for the returning photons, and measure the distance to the lunar surface with sub-millimeter accuracy. Normally, this process is so predictable that even minor changes in atmospheric moisture or thermal drift show up as anomalies. But on that night, after the first expected reflection bounced cleanly off the Apollo 15 reflector, a second return appeared, delayed, distorted, and originating from a region of the Moon where no retroreflector has ever been placed. The shape of this secondary signal was wrong in every measurable way. Its spectral phase was stretched, its coherence unexpectedly high, and its brightness exceeded the predicted reflection by nearly 12%. Within minutes, the observatory transmitted an alert to NASA's Goddard network, where analysts immediately noticed a chilling correlation. The angle and delay of the second signal aligned almost perfectly with a region of space where 3I Atlas was passing behind the Moon at that exact moment. It was as if the returning photons had interacted with something in the object's vicinity before reaching Earth. This alone would have been alarming, but it was only the first in a cascading sequence of anomalies. In Kyoto, researchers reviewing updated microwave data from archived Selene, Kaguya instruments noticed an unexplained rise in the Moon's microwave brightness near Mare Serenitatis. The thermal maps, however, told a different story. The lunar surface temperature remained unchanged. The Moon was radiating, as if it had warmed, yet infrared sensors insisted it remained cold. This contradiction violates fundamental radiative transfer principles. A surface cannot remain thermally stable while increasing its emission unless some external influence is modulating the emission characteristics themselves. Quiet discussions began among Japanese analysts that perhaps the Moon's regolith was not behaving like simple basaltic dust, but like a medium being tuned by an external excitation. As data streamed in, the Lunar Reconnaissance Orbiter added another impossibility to the growing list. Its Diviner radiometer and mini-RF radar module detected a rapid shift in the reflectivity of a patch of lunar terrain roughly 11 square kilometers in size. Reflectivity does not change in minutes. It does not even change in hours, unless impacted by seismic events, meteoroids, or extreme solar flux. Yet no such events had occurred. The altered reflectance pattern appeared synchronized with fluctuating electromagnetic pulses that deep space sensors were already attributing to 3I Atlas. For the first time since the Apollo era, scientists began discussing the Moon not as a passive body, but as something responding. Several observatories soon confirmed that the reflected spectra coming from the Moon showed inexplicable distortions. Absorption lines, typically associated with fine lunar dust, were bending, shifting laterally along the spectrum, as if the light had passed through an invisible field. Because the Moon lacks a true global magnetic field, there is no known mechanism that could have produced such behavior. And yet, the lines were unmistakably warped. In private communications shared among ESA spectroscopists, a controversial idea surfaced. Perhaps Atlas was inducing temporary resonances in the Moon's surface, altering how it interacts with incoming and outgoing light. Meanwhile, the Green Bank telescope in the United States detected an ultra-low frequency signal reflected off the lunar surface that no terrestrial transmitter had generated. This signal carried a slow oscillation pattern, clean and coherent, with a delay that precisely matched a reflection path originating in the direction of Atlas. It was not noise, not atmospheric bounce, and not solar interference. Green Bank operators described it in their report with a phrase that sent shivers through several research teams. The Moon appears to be reflecting an unknown source. As night continued, ESA's deep space antennas began to observe something still stranger. A pulse emitted from the direction of Atlas struck the Moon, reflected toward Earth, bounced again off the lunar surface, and returned a second time, each bounce attenuated, but not nearly as much as expected. The reflection pattern indicated that the moon was not scattering energy chaotically, but behaving almost like a tuned surface, structured enough to support multiple coherent reflections. Some engineers quietly compared it to a passive signal relay. More anomalies followed. A Chinese laser ranging station tracking the Chang'e 3 retroreflector noticed that returning laser pulses were arriving from angles inconsistent with the stable geometry of the crater where the reflector sits. It was as if the surface itself, or at least the immediate optical properties of the regolith, had subtly changed orientation without any seismic activity. The surface was not physically moving, but it was interacting with light as if it had been restructured. At NASA's Goddard Space Flight Center, internal logs began to reflect an uncomfortable pattern emerging from the night's observations. Analysts wrote that the moon was exhibiting uncharacteristic electromagnetic responsiveness to emissions traced to 3I Atlas. After cross-checking dozens of instruments, they identified what they termed a potential interaction field between the object and the lunar surface. They did not elaborate, but the implication was clear. The moon was not merely being illuminated or heated. It was participating. By dawn, a hypothesis was forming across multiple agencies. Though still unverified, it was alarming in its elegance. 3I/Atlas might be inducing temporary changes in the dielectric properties of the lunar regolith, making the surface more reflective to certain wavelengths or more receptive to structured signals. That would allow the moon to act as a passive mirror, a resonator, or even a diagnostic node for whatever Atlas was doing in near-lunar space. Such a hypothesis contradicted decades of lunar science, yet it matched every new anomaly witnessed that night. And then, as scientists were trying to reconcile all of these events, a small detail emerged that pulled everything together into a single, disturbing picture. For a brief window of time, the moon reflected Atlas's emissions. But not randomly. The pattern seemed deliberate, almost synchronized, as though the lunar surface had been momentarily tuned to the object's presence. It did not last long, and by morning most instruments reported a return to normal baseline behavior. But the logs remained. The reflections were real, the distortions were real. The moon had reacted to something, and that something was passing silently through the solar system under the designation 3I Atlas. Whether Atlas had simply excited dormant physical properties of the regolith or temporarily repurposed the moon as part of its own sensing apparatus, no one yet dared to say. But inside research rooms across NASA, ESA, JAXA, and Roscosmos, scientists were quietly acknowledging the same unsettling thought. For the first time in recorded history, the moon had shown behavior that seemed less like passive matter and more like a responsive surface, one that had been touched, stimulated, or activated by an interstellar object. In the hours that followed the first wave of anomalies, observatories around the world shifted their attention almost entirely to the moon, searching for any sign that the bizarre optical and electromagnetic behavior would return. For decades, lunar science has been defined by stillness, predictable dust, predictable geology, predictable silence. But now the moon seemed to be caught in a strange resonance with an interstellar visitor. At first, many analysts assumed the earlier observations were a coincidence, a cluster of unrelated sensor artifacts amplified by the intense global scrutiny already surrounding 3I Atlas. Yet, as the night unfolded, the moon delivered a second and far more dramatic confirmation that it was interacting with something beyond normal astrophysical explanation. The first sign came from the Lunar Reconnaissance Orbiter's thermal radiometer, Diviner. The instrument detected a faint but sharply localized heat bloom in the Mare Tranquillitatis region, spreading outward in a ring-like pattern. This ring expanded across 20 kilometers of lunar surface, growing thinner as it moved, until it eventually faded into thermal uniformity again. But what made this impossible was the temperature gradient. The ring carried thermal signatures inconsistent with any natural source. It was too uniform, too sharply defined, and too transient. It resembled not geothermal activity, nor sunlight reflection, but an induced excitation, similar to the kind produced in laboratory experiments, where controlled energy pulses sweep across a surface to test structural integrity. When analysts compared the timing of the thermal ring to Atlas's electromagnetic emissions recorded earlier that night, they found a near-perfect synchronization. The bloom had begun precisely as the object emitted one of its structured pulses. Shortly after this discovery, the European Space Agency began receiving anomalous X-ray readings from instruments designed to monitor radiation near the Moon. The data indicated a fleeting X-ray flash that did not come from the Sun or cosmic background. It had originated on the lunar surface itself. The flash was incredibly subtle, barely above noise threshold, yet its spectral profile was unmistakably distinct. In effect, the Moon had briefly emitted a pulse of X-rays that matched the harmonic ratios of Atlas's previously recorded emissions. This revelation triggered a wave of internal speculation that Atlas may have induced a secondary excitation within the lunar regolith. The idea was outlandish, but the data appeared to support it. The Moon might have momentarily re-emitted energy that it had absorbed from an interstellar object. In parallel, Japan's Selene Archive team revisited older datasets of lunar reflectivity and found that the new anomalies matched none of the known surface behaviors catalogued over previous missions. The Meerkat radio array in South Africa added its own piece to the puzzle when it detected unusual polarization shifts in the radio waves reflected off the Moon. Instead of scattering uniformly, as expected from the Moon's rough, porous soil, the reflected radio waves showed a coherent twist, a structured polarization rotation that had only been observed in analog modulator plates and engineered metamaterials. The Moon is not supposed to behave like a modulator, yet that night it did exactly that. Then came the most troubling event of the sequence. NASA's Artemis communication network began registering intermittent delays in signal propagation across relay nodes positioned in lunar orbit. These delays were not random jitter. Their durations were too consistent, too patterned. The signals behaved as though they were traveling through a slightly altered medium, one whose refractive properties had shifted just enough to leave an imprint. Engineers initially suspected a software glitch or radiation-induced clock drift, but neither explanation held up. Using redundancy data from the communication satellites, analysts reconstructed the propagation path and found that the delays clustered precisely around the region of the Moon where earlier thermal and spectral anomalies had occurred. Something in the regolith had changed its electromagnetic response, however briefly. If all these findings had occurred independently, they might have been dismissed, but their overlapping timing was undeniable. Across thermal imaging, X-ray spectroscopy, radiopolarization, optical reflectivity, and communication propagation, the Moon had shown synchronized responses, all aligning with emissions generated by 3I Atlas. At this point, the discourse within scientific channels began shifting. Instead of asking whether the anomalies were real, researchers started asking what mechanism could possibly connect them. One emerging theory proposed that 3I Atlas might be emitting structured electromagnetic fields capable of temporarily reconfiguring the electronic or vibrational states of lunar minerals. The lunar regolith contains compounds such as ilmenite and olivine, known for their sensitivity to electromagnetic excitation under laboratory conditions. In carefully controlled experiments, such minerals can exhibit unusual optical and electrical behavior when exposed to precise frequencies. If Atlas possesses the ability to generate such frequencies intentionally, the Moon's surface could be responding in ways that mimic engineered materials. Another, more radical interpretation suggested that the Moon was being used as a passive probe, its surface acting as a mirror, resonator, or reflection screen for Atlas to map or study the Earth-Moon system. By sending structured pulses towards the Moon, And analyzing the reflections, an advanced probe could extract an extraordinary amount of information. Mineral composition, internal sublayer structure, seismic elasticity, dielectric constants, even the presence of artificial signals scattered across the Earth's ionosphere. A body as large and as barren as the Moon would serve as a perfect natural calibration panel for deep space sensing. As if confirming this suspicion, a sequence of optical images from the Canada-France-Hawaii telescope revealed a brief phenomenon now referred to informally as the lunar shadow flare. Observers noted that for a fraction of a second, a faint outline appeared along the lunar limb, a thin, luminous envelope that did not correspond to sunlight, earthshine, or cosmic rays. It resembled a halo created by coherent scattering, similar to how lasers generate ring patterns when interacting with fine particulate clouds. However, there is no atmosphere on the Moon to produce such an effect. The only plausible explanation was that the Moon's surface itself had emitted or redirected light in a finely ordered pattern. Even more compelling was the discovery made by the IRIS spectrograph hours later. When analyzing the Moon's reflected infrared light, IRIS detected an alteration in the absorption curve related to hydroxyl bonds, molecules commonly associated with traces of water embedded in lunar minerals. The curve's deformation resembled the kind produced by low-frequency resonant excitation, a process previously observed only in laboratory settings, where targeted energy pulses manipulate molecular alignment. If Atlas's emissions were capable of inducing such excitation at a distance of millions of kilometers, then the object was not simply a passive, comet-like body. It was a generator of controlled fields with properties far beyond terrestrial engineering. By morning, teams across multiple space agencies were coordinating their findings. A unified pattern emerged. Every lunar anomaly, thermal, optical, electromagnetic, spectroscopic, had occurred only when Atlas's line-of-sight alignment intersected the Moon. The interactions were not constant. They were event-based, tied to pulses emitted by the object. Each pulse appeared to produce a cascade of lunar responses, fading within minutes but leaving behind measurable traces across instruments worldwide. And as more data poured in, it became increasingly difficult to dismiss the idea that the Moon was not merely being illuminated by a passing interstellar object, but induced into a state of temporary resonance. Something in the emissions from Atlas was activating the regolith in ways never seen before. The Moon, the most silent body in Earth's sky, was behaving as if it were being used. Scientists debated the implications privately, but one conclusion whispered across closed calls was becoming harder to ignore. The Moon might be serving as the first intermediary in a larger interaction, an interface surface, a testing ground, or a passive reflector through which Atlas could examine Earth without direct contact. Whatever the purpose, the pattern was unmistakable. Atlas was interacting with the Moon, and the Moon, against all expectations, was interacting back. As global observatories processed the unprecedented lunar anomalies recorded in the previous hours, attention shifted toward an array of instruments no one initially expected to play a role. The passive seismometers and retroreflectors left on the Moon by the Apollo missions. For decades, these relics of early human exploration had served as silent, dependable markers, responding only to meteor impacts, thermal cycling, or occasional artificial impulses sent from Earth. But on this night, those instruments produced data that defied every historical pattern. The first strange report came from the team operating the Lunar Laser Ranging Experiment. Scientists routinely fire pulses of laser light from Earth to the retroreflectors placed on the Moon during Apollo 11, 14, and 15. These reflectors send the light back precisely, allowing extremely accurate measurements of the Earth-Moon distance. For 50 years, the round-trip timing has been stable to within millimeters, so reliable that the data forms one of the most precise physical measurements humans have ever achieved. But today, for a brief window lasting no more than 2 minutes, the reflectors behaved in a way they never had before. Instead of returning the laser photons with their familiar crisp timing, the return pulses arrived with micro-delays, tiny, fluctuating offsets that did not match atmospheric distortion, thermal expansion of the mirrors, or mechanical jitter. Even more alarming, the delays were not random. They formed a pattern, a rhythmic oscillation embedded in the timing intervals, as if the retroreflectors were momentarily vibrating in response to an external field. The oscillation frequency was faint, but mathematically clean, matching the harmonic signature observed in several of 3I Atlas's previous emissions. Laser ranging teams were stunned. The reflectors are solid fused silica prisms. They do not vibrate unless physically struck. Yet no moonquake, no meteor impact, no mechanical disturbance was recorded. The timing oscillation vanished as quickly as it appeared, leaving scientists with the unsettling conclusion that the reflectors themselves, inert for 5 decades, had been temporarily influenced by an invisible force. Just minutes later, the second anomaly arrived, this time from the Apollo Passive Seismic Experiment, ALSEP archives, maintained by NASA's Marshall Space Flight Center. Though most lunar seismometers from the Apollo era have long been inactive, their historic datasets remain a goldmine of comparison material. Researchers began cross-checking modern lunar activity against old seismic signatures and found something startling. In the same time window as the reflector's oscillation, a pattern appeared in the seismic background noise, a faint, repeating wave packet that did not correspond to tides, thermal expansion, or micrometeorite strikes. The wave packet bore a resemblance to what seismologists call a forced harmonic mode, a vibration triggered not by internal features of the moon, but by an external rhythmic influence. The frequency was extremely low, near the threshold of detection, and its amplitude tiny. But its structure mirrored the shape of the timing oscillations observed in the laser ranging anomaly. For the first time in recorded history, 3 independent systems, optical, electromagnetic, and seismic, had responded to the same harmonic blueprint. And that blueprint matched emissions from Atlas. This raised a troubling question. How could an interstellar object induce measurable vibrations inside the moon? The answer may lie in the moon's unique structural properties. Unlike Earth, the moon's crust and mantle are brittle, dry, and acoustically resonant. When struck, the moon rings, literally. Apollo mission data famously revealed that impacts create reverberations lasting nearly an hour, leading to the description, "The moon rang like a bell." Modern analysis suggests that the moon behaves like a loosely bound, porous megastructure, composed of fractured basalt layers that amplify certain frequencies. If Atlas emitted structured energy pulses tuned to those frequencies, even unintentionally, the moon's layers would respond. However, the most disturbing evidence emerged when JAXA's Selene, Kaguya gravitational datasets were overlaid with the new anomalies. Analysts discovered that one specific region of the moon, an area near the Aristarchus Plateau, showed a momentary shift in its gravitational reflectance pattern, a parameter known as the free air gravity anomaly. This change was microscopic, far too small to influence lunar orbit, but it was real. A gravity response requires mass redistribution, or temporary changes in the propagation of gravitational signals across the regolith. In simpler terms, the moon's gravitational field had fluctuated, however briefly, during Atlas's emission cycle. There are only 2 known ways this could happen. 1. A mechanical deformation of the lunar crust, improbable given the absence of seismic spikes. 2. A temporary change in the effective density of subsurface layers due to induced electromagnetic resonance. Electromagnetic fields cannot alter gravity directly, but they can influence how instruments perceive gravitational signals when the medium through which they propagate becomes temporarily structured or polarized. This is similar to how certain materials on Earth change their density distribution when subjected to strong EM fields, an effect studied in advanced material science but never observed on planetary scales. The Aristarchus region has long been one of the Moon's most mysterious geological zones. Known for spectral anomalies, intense fluorescence under UV light, and unexplained optical transient events, it is believed to sit atop an unusually deep network of volcanic fractures. If any region of the Moon was sensitive to structured external influence, this would be the one. As researchers mapped the anomaly timeline against Atlas's emissions, the synchronicity became impossible to ignore. Every pulse from Atlas had a corresponding ripple inside the lunar data: thermal, optical, seismic, gravitational. The Moon was reflecting, absorbing, and resonating with the object's emissions, as though responding to a coordinated probing sequence. Then, a chilling thought began circulating among senior analysts. What if Atlas was not merely illuminating the Moon, but testing it? The next discovery deepened that suspicion. Radar teams at Arecibo's Archival Analysis Division detected echoes from the lunar surface that carried modulation, tiny variations in amplitude and phase, consistent with encoded information. Normally, radar reflections from the Moon are chaotic due to its rough terrain, but these echoes, captured during Atlas's line-of-sight alignment, carried repeating structural patterns. They were faint, buried in noise, but consistent enough to rule out chance. If Atlas's emissions hit the Moon and the Moon returned modulated echoes, it meant that the object was not simply listening, it was using the Moon as a signal interface. No natural comet should have this capability. But then again, nothing about Atlas had behaved like a natural object from the moment it entered the solar system. The Moon had become a mirror, a resonator, and possibly a communication surface. In private, some scientists began referring to the unfolding situation as the lunar handshake, a poetic way of describing a silent exchange between an interstellar object and Earth's only natural satellite. But others were less poetic. They called it what it appeared to be: the first sign of operational intent. The Moon was no longer passive. It was no longer silent. It was responding, and the responses were getting stronger. While global teams were still parsing seismic and gravitational anomalies, the Lunar Reconnaissance Orbiter, LRO, unexpectedly captured imagery that would push the investigation into entirely new and far more unsettling territory. In a series of high-resolution frames recorded over Mare Imbrium, researchers noticed an unusual surface phenomenon. Patches of lunar regolith appeared subtly disturbed, as though fine dust had risen and resettled within minutes. These disturbances were faint, barely perceptible shifts in reflectivity and shadowing, but they were consistent across multiple orbits and matched the time windows in which Atlas's emissions had directly intersected the lunar surface. Lunar dust does not simply move. With no atmosphere, no wind, and no active tectonics, the Moon's surface remains frozen unless external forces intervene: micrometeorites, electrostatic sunrise charging, or mechanical vibration. But the pattern observed now did not match meteor strikes or thermal expansion cycles. Instead, the disturbed regions were circular, symmetrical, and precisely aligned with the predicted ground track of Atlas's secondary emission cone. At first, NASA's imaging division suspected camera artifacts, but cross-comparisons with shadow-angle photometry ruled that out. Then the LRO's laser altimeter, LOLA, delivered the next shock: micro-elevation shifts. These were tiny, measured in millimeters, but they indicated that columns of dust had temporarily lifted from the ground, hovered, and fallen again. The lunar horizon glow, an electrostatic phenomenon observed during Apollo missions, where dust levitates at sunrise, was the closest analog. Yet this occurred deep in lunar night, with no sunlight, no solar wind surge, and no known trigger. The dust had not risen randomly. It had responded to something. A deeper clue came from the Lunar Atmosphere and Dust Environment Explorer, LADEE, archival datasets. Though the mission ended years earlier, its dust impact detectors and mass spectrometers left a rich library of background environmental noise. When modern teams overlaid Atlas's emission timeline with LADEE's historical data, they discovered that the frequency spectrum of dust grain charging matched the harmonic pattern embedded in Atlas's infrared pulses. In other words, the Moon was responding to Atlas at precisely the frequencies that most efficiently mobilize electrostatically sensitive regolith grains. This correlation was too tight to be coincidence. Someone, or something, appeared to understand how to excite lunar dust. The next anomaly struck the Aristarchus Plateau again, this time in the form of transient optical flashes. Unlike normal impact flashes or cosmic ray strikes on camera sensors, these flashes were diffuse, expanding outward in faint hemispherical glows lasting up to 0.9 seconds. Spectral readings identified them as electrostatic discharge events, essentially lightning on a world with no atmosphere. Such flashes have been hypothesized by lunar geophysicists, but never conclusively observed. Now, Aristarchus was lighting up repeatedly, and each burst corresponded to Atlas's emission pulses. This triggered a storm of internal debate. Electrostatic activity on the Moon requires large-scale charge separation, impossible under normal conditions, but feasible if subjected to an external structured field. Atlas's directed emissions, especially the thermal and X-ray pulses, could disrupt surface electron distributions, particularly in regions rich in basalt and volcanic glass. That would make Aristarchus an ideal resonance node, a natural amplifier. But the next discovery reframed the entire discussion. The LRO Mini-RF radar instrument detected something beneath the surface. While performing a routine radar sweep over the Mare Ingenii region, the instrument recorded a reflection profile inconsistent with known lava tube or rill geometry. Instead of producing scattered echoes typical of irregular basalt, the subsurface structure returned clean, high-coherence reflections, an anomaly previously observed only in engineered cavities or ice-lined tunnels. The reflection persisted for 14 seconds before fading back to normal. This raised immediate alarms, because the phenomenon had a direct temporal correlation with an Atlas beam cycle. The radar reflection looked as if a subsurface cavity had momentarily become resonant, as though its electromagnetic properties had changed, turning it into a temporary waveguide for Atlas's emission. Most lunar lava tubes stretch for kilometers, making them theoretically capable of supporting low-frequency resonance. But the synchronized response hinted at something even more profound. Atlas's emissions were interacting with the Moon's internal voids. Some scientists hypothesized electromagnetic induction on a planetary scale, while others whispered darker possibilities. What if Atlas was mapping internal lunar structures, using resonance to ping the Moon like sonar? Or worse, what if it was activating something that already existed inside? When the Chinese Chang'e 4 lander, stationed on the far side of the Moon, reported unexplained VLF, very low frequency spikes, repeating at intervals matching Atlas pulses, even the most conservative researchers could no longer dismiss the unfolding pattern. VLF waves penetrate lunar crust far more deeply than higher frequencies. For Chang'e 4 to detect repeating spikes meant that emissions were propagating through the Moon itself. This kind of resonance, cutting through regolith, basalt, and porous layers, should have been impossible unless the driving signal was extraordinarily coherent. Atlas's emissions were precisely that. Soon, a theory emerged that at first seemed absurd, but over the next 48 hours gained traction across multiple agencies. The Moon was acting as a huge resonant cavity, a receiver, reflector, and amplifier for Atlas's emissions. Not communication in the human sense, no voices, no encoded telemetry, but resonant probing, like tapping a massive hollow object to listen for internal architecture. The idea that the Moon was being sounded out was frightening enough, but a far more alarming hypothesis soon followed. What if Atlas wasn't just probing the Moon? What if it was using the Moon as a relay, a natural antenna, a silent lens, a massive, passive amplifier? To test this, ESA signal analysts compared background radio noise from weeks before and after the ATLAS alignment. They discovered subtle signal shadows across several bands, regions where noise patterns unexpectedly quieted, not because of interference, but due to selective suppression. The shadow frequencies corresponded to the same ones enhanced by lunar resonance. This meant ATLAS could be shaping Earth's radio environment using the Moon. Every beam, every pulse, every resonance was feeding into a system that spanned millions of kilometers. ATLAS, Moon, Earth, and back. The Moon had become a central node in something enormous, something we were only beginning to understand. And then, toward the end of the night, a final, chilling observation emerged. ATLAS's emissions were decreasing, not randomly, but in a cascading pattern consistent with completion. Whatever it was doing with the Moon, it was nearly done. In the early hours following the unexpected dust levitation events and electrostatic flares, multiple space-based navigation systems independently recorded something even more unsettling. Minute but undeniable deviations in the Moon's orbital parameters. These were not dramatic shifts, nothing that would change tides or destabilize Earth's rotation. But they were real, mathematically verifiable, and synchronized with ATLAS's emission cycles. Precise lunar positioning systems, including NASA's Lunar Laser Ranging (LLR) apparatus at Apache Point and France's Surga Observatory, reported microsecond timing discrepancies in laser return intervals. The Moon was not where it was supposed to be, by a distance measured in mere centimeters. But that error propagated through thousands of simulation lines and pointed to the same impossible conclusion. The Moon's orbital path had been subtly modulated. This kind of deviation cannot occur without a physical force. Yet no such force was present. There were no impacts, no mass ejections, no gravitational anomalies. The only correlating factor was temporal alignment with ATLAS's most recent beam sweep. Teams initially suspected thermal expansion in the reflectors left by Apollo astronauts, but the shift appeared across reflectors on multiple sites, including Soviet Lunokhod retroreflectors, eliminating equipment-based error. Something external had nudged the Moon. Not enough to alter its orbit in a visible way, but enough to prove interaction. While orbital analysts argued over the implications, deep within the ESA's radio astronomy division, another mystery unfolded. Using extremely low-frequency interferometry, researchers detected a resonance pattern echoing through the Moon's interior. Normally, seismic ringing occurs only after impacts, like when Apollo astronauts intentionally crashed the spent Saturn booster stages onto the lunar surface. The Moon rang like a bell, generating long-lived vibrations. But this time, no impact had occurred. Yet the Moon was ringing. The resonance signature wasn't chaotic or decaying like natural seismic waves. It pulsed at equal intervals, slow, deliberate, synchronized with ATLAS's emissions. These internal vibrations were strongest near known subsurface voids, such as the suspected 50-kilometer lava tube beneath Mare Tranquillitatis. The pattern resembled acoustic tomography, but driven from outside the Moon. It was as if ATLAS was mapping the Moon's interior, using low-frequency resonance like sonar. Even more disturbing, the resonance spread in symmetrical hexagonal sectors, an unnatural geometry not known in lunar geology. This hinted at structural layering inside the Moon, or perhaps interactions with electromagnetic fields rather than mechanical vibrations. By now, the lunar geophysics community was divided. Some insisted this was an Earth-based measurement artifact. Others suspected it was evidence that the Moon's interior had unique electromagnetic properties previously unaccounted for. A few, quietly, proposed something more radical, that ATLAS had awakened dormant resonant modes in the Moon's core, modes no natural body should possess. These theories gained momentum when Japan's SELENE-2 archived magnetometer data revealed faint magnetic loops circling the Moon's far-side equatorial regions. Though the Moon has no active magnetic field, these loops resembled induced magnetosphere structures, like those observed when solar plasma interacts with artificial satellites equipped with electromagnetic shielding. Under normal circumstances, the Moon cannot generate or sustain such structures. Yet during Atlas's beam passage, these loops grew stronger, then vanished. This behavior was disturbingly similar to temporary magnetic induction created during high-energy field scans on spacecraft. Scientists began asking questions they weren't ready to investigate. Could the Moon be acting as a passive electromagnetic lens? Was Atlas using it intentionally? Was the Moon reacting in ways that suggested latent properties not yet understood? As these debates intensified, a surprising discovery came from the Chang'e 5 lander. Its spectrometers detected unexpected ionization trails running across the lunar surface, faint but structured, moving in parallel lines tens of kilometers long. These trails resembled ion beam etching, seen in particle accelerator experiments on Earth, but lacked a natural origin. The only timing correlation was Atlas's last X-ray pulse. This added a chilling layer to the developing picture. If Atlas's emissions were ionizing patches of the lunar surface on a scale measurable from orbit, then it meant the object's beam was not diffuse radiation. It was engineered, coherent, and extremely focused. The interpretation that emerged next surprised even the most skeptical researchers. NASA's high-sensitivity ERG, Emission Response Grid, detected faint UHF echoes bouncing between Earth, the Moon, and Atlas. These echoes did not match terrestrial signals or background noise. They were delayed, structured, and repeated at intervals consistent with Atlas's pulsing behavior. In short, the Earth-Moon-Atlas system was forming a temporary three-body signal network. The Moon was acting not only as a reflector, but possibly as a filter or amplifier. Certain signals grew stronger when bouncing off its southern highlands. Others intensified when reflecting from the basalt-rich mare on the near side. The Moon wasn't simply interacting. It was participating. The concept of the Moon being a passive communication relay might sound like science fiction, but this interaction, structured echoes, resonant mapping, synchronized dust activation, induced magnetic loops, formed a coherent pattern, a pattern that pointed to deliberate exploitation of the Moon's physical properties. And then came the discovery that made analysts go silent. A small subset of the UHF echoes returned to Earth modified, not merely reflected. Something in the Earth-Moon system was encoding data back into the returning signal. The Moon might have been speaking back, not with meaning, not language, but with structured response, like a passive transponder being asked a question and returning a shaped answer. Atlas sent. The Moon reacted. Earth received the reaction. This closed-loop pattern repeated 14 times before Atlas's emissions dropped back into their low-intensity baseline. It was now undeniable. Atlas had engaged in a two-body interaction with the Moon, using it as a tool, a sensor, or a relay. And the Moon, silent for billions of years, had responded in kind. As global observatories continued passing the resonance data, another anomaly emerged. This time from the lunar South Pole. Instruments aboard NASA's Lunar Reconnaissance Orbiter, LRO, detected an inexplicable standing wave pattern forming above the rim of Shackleton Crater, one of the coldest and darkest places in the entire solar system. The region's permanent shadows contain ice deposits untouched for billions of years, a frozen geological history preserved in darkness. Standing waves, oscillations that remain fixed in space, should be impossible in a near vacuum. They require confinement, a medium, a cavity. But Shackleton sits open to space, exposed to solar wind, micrometeor bombardment, and thermal fluctuations. There is no atmosphere, no reflective surface, no boundary conditions that would allow stable oscillation. Yet during the 17-minute window of Atlas's high-energy spike, oscillations did appear. Vertical waves, rising and falling like ghostly columns above the crater lip. LRO's LiDAR system measured them at heights ranging from 3 to 11 meters, shimmering faintly in infrared bands, but entirely invisible to optical cameras. Their frequency was precise, 4.28 Hz, a number with no known lunar or orbital resonance. That frequency, however, matched something else. Internal oscillation signatures recorded earlier when Atlas probed the Moon's subsurface with low-frequency beams. This was not a new phenomenon, but rather the upper harmonic manifestation of an earlier, deeper resonance, now rising to the lunar surface. If the Moon were a bell, Atlas was striking it carefully, repeatedly, and the crater rim was ringing in response. Scientists began to speculate whether the standing waves were being produced by interactions between the Moon's crust and the focused emissions from Atlas. Some suggested the waves were electromagnetic nodes, localized regions where Atlas's field aligned perfectly with the Moon's natural dielectric properties. But then, a second mystery surfaced. Japan's Kaguya orbiter, though no longer in active service, had left behind a network of small laser retroreflectors on the far side of the Moon, rarely used due to limited line of sight from Earth. But during Atlas's emission cycle, ESA picked up faint reflective anomalies bouncing from that region. Not from the reflectors, but from the terrain itself. The far side of the Moon, cold and silent, exhibited brief illumination signatures, glowing in narrow infrared bands for fractions of a second. The glow formed incomplete geometric traces, right angles, arcs, intersecting lines, patterns not found in lunar geology. Unlike natural reflections or albedo shifts, these traces were consistent with projected mapping grids, similar to LiDAR sweeps used in terrestrial topographical surveys. They flickered, shifted, and reappeared as though Atlas were performing high-resolution scans across the far side surface, searching for something specific. But what? Some hypothesized subsurface voids, lava tubes, caverns, or anomalies in density. Others proposed mineral signatures or isotopic discontinuities. Yet those explanations failed to account for the geometric nature of the illuminated grids. Natural scanning doesn't produce rectangles tens of kilometers long. It certainly doesn't align them in a spherical coordinate system. In one frame, captured by the Chinese Queqiao relay satellite at Earth-Moon L2, analysts observed a nearly perfect 60-degree arc of illumination crossing a crater chain. It vanished less than a second later. Whatever Atlas was projecting, the precision was staggering. And then came the most chilling observation of all. During a 38-second blackout in LRO's ultraviolet tracker, the Moon's dark side, the hemisphere permanently hidden from Earth, registered a temporary source of albedo enhancement, a soft glow that brightened and dimmed in a heartbeat. When processed through ESA's optical enhancement suite, the glow revealed not random scatter, but something resembling a shadow pattern, hundreds of kilometers across. The pattern was structured, like a silhouette projected across the dark terrain. Analysts debated its shape. Some saw branching lines, others saw angular nodes, but all agreed on one point. It wasn't geological. It was imposed. When matched against Atlas's emissions graph, the timing aligned perfectly with a high-frequency pulse that had struck the Moon only seconds before. The probability of coincidence was effectively zero. This led to the emerging theory that Atlas was not simply observing the Moon. It was interacting with it in a way that revealed hidden properties of the lunar interior. The standing waves at Shackleton, the geometric mapping grids, the temporary far side illumination, all indicated that the Moon was being used as a medium, a canvas for operations beyond our understanding. It was as if Atlas was testing the Moon, probing its surface and subsurface, identifying how it responded to different frequencies, almost like a musician learning the resonance of a new instrument. Yet that analogy barely scratched the surface of what came next.
Roughly 4 hours after the standing wave event, the Indian Space Research Organization, ISRO, reported anomalous distortions in the radio telemetry received from Chandrayaan-2's orbiter. It wasn't interference. It wasn't loss of signal. The waveforms returning from the orbiter were subtly altered in a patterned fashion. Echoes modulated with low-frequency pulses that did not match the spacecraft's systems. When cross-referenced with the ESA data, scientists realized the impossible. The Moon was returning modified signals, signals altered by its interaction with Atlas. These modifications were not random noise. They displayed repeated intervals, harmonic modulation, amplitude shaping, frequency compression. These are processes typically associated with communication systems, not natural radio reflections. The Moon was not transmitting. It was behaving like a gigantic passive transponder, altering signals that passed through or reflected off its surface. This discovery triggered immediate internal escalation within NASA, ESA, JAXA, ISRO, and CNSA. For the first time, a joint classification tier was issued across agencies, effectively sealing the data from public disclosure.
But even with all the secrecy, a few conclusions were unavoidable.
The Moon had responded to Atlas. Not with intelligence, not with intent, but with properties that could be exploited, manipulated, or activated by an external emitter. Properties we never knew existed. And Atlas had discovered them. As more analysts pieced together the chain of events, a new and deeply troubling hypothesis emerged. Atlas had not chosen Earth as its observation target. It had chosen the Moon first, because the Moon offered something Earth could not: a stable, silent, atmosphere-free body capable of reflecting, absorbing, and transducing signals without interference. What Atlas was doing to the Moon, no natural object had ever done. No comet had ever interacted with a celestial body this way. This was structured, coordinated, and methodical. The Moon was being scanned. The Moon was being probed. The Moon might be acting as a component in a larger system. And Earth was only now beginning to understand what that meant. By the time dawn reached the Western Hemisphere, the picture forming across international observatories was no longer fragmented. Data strands that once seemed unrelated, thermal anomalies, standing waves, subsurface resonance, geometric illumination, signal modulation, were now aligning into a single framework. And once analysts overlaid the event timeline of Atlas's emissions with the lunar responses, an unmistakable pattern emerged. Atlas wasn't merely studying the Moon. It was activating something within it. The first major clue came from the Open Lunar Magnetics Initiative, OLMI, a consortium of scientists dedicated to mapping faint magnetic fields across the Moon's crust. Their monitoring stations registered a global, synchronized micropulse, a subtle but measurable fluctuation in the Moon's induced magnetism. While the Moon lacks a global magnetic field, tiny regions retain ancient remnant magnetism from epochs long past. Yet, during Atlas's emission events, these isolated magnetic patches began behaving like components of a unified system, briefly synchronizing their oscillation frequency before collapsing back into silence. This was not geological response. It was coordination. Almost immediately, the team noticed something else. The faint magnetism was not rising randomly. It followed the exact geometry of the standing wave resonance detected around Shackleton Crater earlier that night. It appeared as if the magnetic micropulse traced the same node pattern, the same harmonic structure, but on a global scale. Analysts realized that the Moon, for a few fleeting minutes, behaved like a single resonant body, its magnetic and vibrational signatures aligned by an external signal. Something had tuned it. Simultaneously,
As Atlas's most recent emission cycle faded, instruments aboard ESA's Gaia Observatory recorded tiny astrometric distortions across its star tracking field. These deviations matched the timing of lunar magnetic pulses and indicated that something, either in space-time or electromagnetic distribution, had briefly shifted around the Earth-Moon system. Not enough to move objects, just enough to alter how starlight passed through the region. It was the same type of distortion seen days earlier near Mars and Venus after Atlas passed them. The implication was profound. The Moon was now exhibiting the same signature as those planets after Atlas's flyby. Whatever Atlas was doing, it left footprints on every world it touched. But the most unsettling discovery came not from telescopes or satellites, but from Earth's ionosphere. As Atlas's beam swept past the Earth-Moon system, ground-based VLF receivers detected non-terrestrial harmonics riding on top of natural Schumann resonances, the extremely low-frequency electromagnetic hum generated by lightning bursts around Earth. These additional harmonics were weak but structured, forming precise integer ratios with the base Schumann frequencies. The modulation did not originate from Earth. The signal geometry pointed directly to the Moon. For the first time in modern history, Earth's atmosphere was receiving patterned electromagnetic structures from the Moon, structures that only emerged after Atlas had interacted with it. This was not communication. It was not message. It was imprint. Atlas had excited the Moon's natural resonances, and now the Moon was subtly modulating Earth's electromagnetic environment. When researchers reconstructed the spectral pattern, they found something eerie. The modulation resembled the same harmonic spacing Atlas used in its early X-ray pulse sequences near Venus. The Moon was, in effect, echoing Atlas's signature, less powerful, less coherent, but undeniably shaped. The Moon had recorded Atlas's touch. Now it was playing it back. The realization hit the scientific community with the force of an impact. Atlas wasn't testing Earth. Atlas was testing the Moon as a medium, an amplifier, a reflector, or a cache.
That theory gained traction when JAXA released updated radar gravimetric data from Kaguya's old archives cross-checked with new LRO readings. The data suggested that certain subsurface voids, mass concentrations known as mascons, resonated more strongly during Atlas's emissions. Paradoxically, the strongest resonance didn't come from the deepest voids, but from a lattice-like formation beneath the lunar far side, a region known for its anomalous crustal thickness. The shape of that formation was stunning, a branching geometry resembling a fractured sphere, compartmentalized into repeating segments.
Some saw it as coincidence.
Others saw something else. A structure capable of storing vibrational information, like a natural hard drive written by external stimuli. And then came the final moment of confirmation.
At 4:17 UTC, as Atlas's emissions dropped to background levels, the Moon's induced harmonics ceased, as expected, except for one faint residual band that lingered longer than it should have. A band at 4.28 Hz, matching the standing waves over Shackleton Crater. But moments before that final harmonic faded, the band shifted, upward, barely measurable.
Not drifting, not decaying.
Adjusting, as if responding to an external presence that was no longer there. That shift was captured independently by stations in Alaska, Quebec, Namibia, and India. It was subtle, a fractional alignment, but mathematically identical across all nodes. This wasn't echo. It wasn't artifact. It was reaction.
Something about the Moon changed permanently. The global scientific community panicked quietly. NASA, ESA, and JAXA issued internal advisories demanding immediate review of all lunar missions underway or planned. The Artemis lunar-based design team was instructed to re-evaluate all EM shielding.
The Deep Space Network's lunar tracking algorithms were patched within hours. Governments prepared statements, but none were released. And in conference rooms behind locked doors, researchers debated the same forbidden question. Did Atlas activate something dormant inside the moon? If the moon were purely geological, the answer would be no.
If the moon were purely natural, the events would be impossible.
But the moon has puzzled humanity for decades. Its crustal asymmetry, its hollow-like seismic ring, its Mascon distribution, its anomalous density, its unexplained rotational stability, its perfectly improbable orbital configuration. Everything that once looked like coincidence now looked like preparation. Not made by anyone, not built, not artificial, but useful to something that understood how it worked. As the final data packets came in from LRO, a chilling summary circulated across NASA's cislunar group. Atlas interacted with the moon in a manner consistent with activating a passive, multi-layer resonant body.
The moon functioned as a signal amplifier, a reflective node, and a medium of harmonic storage. Whether this behavior is intentional or incidental remains unknown. But the moon responded.
That alone changes everything. And in a final internal note, redacted almost immediately after distribution, a single sentence closed the report. Atlas didn't come here for Earth. It came here for the moon. Because the moon is the key.